During the last lecture, we examined the issue of stationary versus non-stationary data. One thing that we did was to examine the properties of stationary versus non-stationary series, and then we investigated what would be the consequences if we use non-stationary data in their raw or levels forms. We said as well that the most empirically relevant form of non-stationarity is a stochastic form of non-stationarity. And such a series could be characterised as being drawn from a random walk or a random walk with drift. Now, if we take the random walk with drift or the random walk model and we write that out, it would look, for example, as yt equals yt minus 1 plus ut. Then we know that we can create a stationary series from this by applying the first difference operator once. So if we constructed delta yt, which is yt minus yt minus 1, then obviously that's just going to equal ut, which by assumption is just a stochastic disturbance term with all the usual properties we assume of such a disturbance term. We can now define a new piece of notation where we would say that our original series yt was integrated of order 1. So we would write yt is integrated of order 1. What does that mean? That means that our original series yt contains one unit root and requires application of the first difference operator once to induce a stationary series. If yt is integrated of order 1 and we use this notation, then obviously delta yt, which is the first difference of yt, is integrated of order 0. In other words, delta yt doesn't contain any unit roots at all because it's a stationary process. In other words, we don't need to take first differences of delta yt to get a series that is stationary. More generally, we can view this as being one special case of a more general framework that we could have. If we had a series y which was integrated of some order d, where d is obviously a positive integer, then that would mean that that series y had to be difference d times in order to get a series that is stationary. Now it turns out that in economics and finance, the vast majority of series that are of interest to us are typically I1 in their levels forms. In other words, they contain exactly one unit root. There is, however, one series which some researchers think may contain two unit roots, and that series is a series of consumer prices measured over time. For example, if we had time series observations on the retail price index. Now, you might then ask the question, what would an I2 process look like? In other words, what kind of equation could we write down for an I2 process? Well, the answer is an I2 process might look as follows. An I2 process we may be able to write as yt equals 2 yt minus 1 minus yt minus 2 plus ut. And it turns out that in that case, yt is integrated of order 2. In other words, we need to apply the first difference operator twice in order to get a series that's stationary. To see why that is the case, consider applying the first difference operator once as we did before. In other words, consider forming delta yt, which is yt minus yt minus 1. If we form delta yt, that's as if we subtracted yt minus 1 away from both sides of this expression. So obviously we've taken yt minus 1 away from the left-hand side. If we then take yt minus 1 away from the right-hand side, what are we left with? Well, we had two lots of yt minus 1. If we subtract one of those lots of yt minus 1 away, then obviously we'll have one lot of yt minus 1 left at the end. And then obviously we'll have these other bits that we had before, minus yt minus 2 plus ut. Now, if we define delta yt as being the difference between yt and yt minus 1, then obviously yt minus 1 minus yt minus 2 we could view as being delta yt minus 1. In other words, it's exactly the same as what was on the left-hand side here, but with 1 subtracted away from the time subscripts. So we could write delta yt equals delta yt minus 1 plus ut. Now, what we've done here is to take a series that was integrated of order 2, apply the first difference operator once, and what have we ended up with? Well, you can see, hopefully, that this is exactly the same as a random walk in delta yt. So we started off with a process yt that was integrated of order 2, we applied the first difference operator once, and now we've got a series that's integrated of order 1 because this is just a standard random walk model. So we could write delta yt is integrated of order 1. So, in other words, we had a series that contained 2 unit roots. We've removed one of those unit roots by applying the first difference operator. We therefore end up with 1 unit root left at the end. If we wanted to make a series that was stationary from this, then what we would have to do is to apply the first difference operator a second time. In other words, we'd have to construct delta squared yt, or delta yt. If we did that, if we applied the difference operator one more time, then we'd end up with a stationary series. So more generally, if a series yt contains d unit roots, we need to apply the difference operator d times in order to make a stationary series. So this kind of exists as a theoretical framework, but as I said, in practice, we only usually believe that series in economics and finance have orders of integration up to I2. We don't ever believe that we find series that are integrated of order 3 or 4 or anything like that. One other thing we discussed during the last lecture was the issue of how we actually determine whether a series is stationary or not. And if we follow what I said last time, which was that the stochastic form of non-stationarity was the most important in practice, then we can test for whether series are stationary or non-stationary by estimating the autoregressive model of order 1 and examining the value of the slope coefficient. So the way that we do that is to take yt and to regress it on its previous value, yt minus 1. And then we investigate the value of this slope coefficient phi or phi. And specifically, we test the null hypothesis that the true value of this coefficient is 1 against a one-sided alternative that it's less than 1. If the value of this coefficient equals 1, obviously then this process for y contains a unit root, or it's a random walk, and therefore we have a non-stationary series. If, on the other hand, we reject this null hypothesis, then we can conclude that we have a stationary series because it doesn't contain a unit root. Now, the early and pioneering work on testing for a unit root in time series was done by Dickey and Fuller, and so this is known as the Dickey-Fuller test. So essentially, we could conduct the hypothesis as it's written here, but it turns out that it's usually easier, instead of running this test regression and testing this null hypothesis, to run a test regression where we regress delta yt on the lag of yt. So all we've done is taken this expression here and subtracted yt minus 1 away from the left-hand side. What will that mean? Well, obviously, if we subtract yt minus 1 from the left-hand side, it also means we have to subtract yt minus 1 from the right-hand side. So therefore, the coefficient we've got here, that psi or psi, must be exactly equal to the phi that we had over here, less 1. So the reason that it's easier in practice to use this test regression rather than this one is that if we use this test regression here, we end up testing instead the null hypothesis that the true value of psi is 0 against a one-sided alternative that it's less than 0. Now, this is easier to do in practice because what that means is that our test statistic can simply focus upon the usual t-ratio of the slope coefficient in this regression. So instead of actually having to calculate the value of the test statistic, we can simply look at the value of the t-ratio, which any regression package will automatically calculate for us. So we calculate the value of our test statistic, which is given by the estimated value of this parameter divided by its standard error, and that is the Dickey-Fuller test statistic. Now, one important thing that we need to note in this context is that there are a number of different forms that we can use for the test regression. And essentially the differences in the forms depend on whether we allow for the possibility of a constant or a constant and a deterministic trend in the test regression. Now, in all of these cases, we're not really interested in the value that the constant parameter or the value of the slope on the deterministic trend will take. We don't care what the values of those are, and it turns out that we can't conduct any hypothesis tests about those values either. All we're doing is allowing for the possibility of their existence in the data generating process. So if there's a possibility that there could be an intercept in the data generating process for y, or an intercept that's not zero and possibly a deterministic trend as well, then we can run test regressions that include these terms, that is, that allow for the possibility of their existence. In all three cases, our test still focuses on the t ratio on this psi coefficient here, or on the test statistic, which would be phi minus 1 divided by its standard error if we ran this test regression. And obviously in both of these two cases we'd have the same test statistic. Also, whether we include a constant or not, or whether we include a constant and a deterministic trend, doesn't impact upon the way that we construct the test statistic. It does, however, impact upon the critical values, as we'll see in a moment. What we should do is to conduct the test excluding a constant and a trend, including a constant but not a trend, and including a constant and a trend. In other words, we should conduct 3 separate tests in every case, and what we would hope is that we end up reaching the same conclusion in all 3 of those cases. That is, we hope in all 3 cases we don't reject the null hypothesis, or in all 3 cases we do. And it turns out, fortunately, in practice that we do usually reach the same conclusion in all 3 cases, especially for large sample sizes. Now, even though the test statistic in both of these 2 regressions takes the form of a very standard t-test statistic, it turns out that we cannot obtain critical values from the usual t-distribution. The reason for that is that under the null hypothesis that we're testing here, whichever these 2 forms for the null hypothesis we use, we've clearly got unit root non-stationarity under the null hypothesis. We saw during the last lecture that the existence of unit root non-stationarity implies that the possibility exists for spurious regressions. And one implication of that is that the test statistics don't follow their standard distributions. So, that being the case, we cannot compare the values of these test statistics with the usual critical values. In fact, we need to compare these test statistics with critical values constructed from a simulation analysis. In other words, there are no analytical formulae that we could use to get the critical values because the test statistics follow non-standard distributions. Now, if we were to examine what the impact of the non-stationarity is on these tests, then, in other words, if we were to actually look at the critical values from the appropriate tables for conducting these Dickey-Fuller test statistics, we can see that the critical values have been made bigger in absolute value than they were previously. Obviously here, in both cases, we're only doing a one-sided test, where the rejection occurs only in the lower or left-hand tail of the distribution. So if the distribution of the test statistic looks something like this, and I'm not saying it follows a normal or a t-distribution, this could be any old distribution for now, obviously the whole of the rejection region would lie in this lower or left-hand tail. So this would be the whole of the rejection region over here in the left-hand tail. And if we used the standard or conventional 5% significance level, then the appropriate critical value for if we included a constant but no trend in the test regression would be minus 2.86. Now, if the test statistic had followed a normal distribution or a t-distribution with a very large degrees of freedom, then the appropriate critical value would have been about minus 1.65. So we can see that in this context, the critical values have been increased substantially in absolute value, or they've been made bigger and more negative by the fact that we've got non-stationarity under the null hypothesis. So the impact of the non-stationarity on the distribution of the test statistic under the null hypothesis has been to make that distribution under the null hypothesis have fatter tails than it did previously. So the distribution of the test statistic for a Dickey-Fuller test has fatter tails than the distribution for if we were just conducting standard hypotheses in the context of stationary data. If we include a constant in the test regression, then the critical values become more negative still. That is, they become even bigger and more negative. And if we include a constant and a trend in the test regression, then the critical values become even bigger and more negative. So if we include a constant, and then if we include a constant and a trend, we need more evidence against the null hypothesis before we would reject it. Technically speaking, this occurs once again because allowing for the possibility of a non-zero intercept or for a deterministic trend in the test regression makes the distribution of the test statistic fatter than it otherwise would have been. And that is because we can think of the estimated intercept and deterministic trend parameters as being what we might call nuisance parameters under the null hypothesis. So the extent to which we estimate these parameters for the intercept and the deterministic trend with error implies that the outcome of the Dickey-Fuller test becomes more uncertain. This results in a widening of the distribution for the test statistic under the null hypothesis and therefore bigger critical values in absolute terms. So the way that we conduct the test is exactly the same as for a standard t-test. That is, we obtain the value of the test statistic, we see whether the test statistic is bigger and more negative than the critical value or not. If the test statistic is more negative than the negative critical value, then we would reject the null hypothesis, and therefore we would conclude that our series was stationary, that we were testing. If, on the other hand, the test statistic was not more negative than the negative critical value, in other words, if the test statistic fell in the 95% non-rejection region, then we would conclude that we don't reject the null hypothesis. And under the null hypothesis, we had a unit root in the series under examination. So that being the case, we conclude that our series had a unit root. Now, unfortunately, matters are complicated somewhat when we actually conduct these tests in practice. The first one of these complications is that the distribution of the test statistic is such that it will only be appropriate to compare this test statistic with the critical values that I've just discussed if the residuals from the test regression are white noise. Now, in particular, if there is some autocorrelation in delta yt, which was not being captured by the model, if you like, that is, it was not captured by the lag of the level of yt. In other words, if there was autocorrelation in delta yt that wasn't being captured by the variable yt minus 1, then we would end up with autocorrelation in the residuals of the test regression. That being the case, then the critical values which we would have examined would no longer be appropriate, and the test statistic wouldn't follow the distribution that those critical values would have suggested. So we could get the wrong conclusions from applying the Dickey-Fuller test in that case. The way that we get around that is to what's called augment the test regression by using lags of the dependent variable. Now, what that means is that we allow in the test regression for the possibility of lags of the first difference of yt to influence the current value of delta yt. So all we do is add lags of the dependent variable into the test regression. Now, the test regression will still focus upon the value of the psi coefficient and its t ratio in particular. All we're now doing is allowing for the possibility of autocorrelation in delta yt in our test regression. So what we can do is add p lags of the dependent variable, that is p lags of delta yt in the test regression, to soak up possible autocorrelation in delta yt to ensure that that autocorrelation doesn't end up being pushed into the residuals of the test regression model. Now, an obvious question to ask, given that, is what is the appropriate number of lags to include in the test regression? It turns out that there are two perfectly valid ways to answer that question. The first one is that by convention, although this is somewhat unscientific and somewhat ad hoc, is that researchers suggest that we can use the frequency of the data to decide the appropriate value of p. In other words, for example, if we had quarterly data, we could use the value of p equals 4, that is, we'd add 4 lags into the test regression. If we had monthly data, we could add 12 lags into the test regression, and so on. Obviously, this kind of rule won't work very well if we've got very high frequency financial data that we were trying to test. For example, if we were trying to examine the minute by minute values of the FTSE index, then that rule wouldn't work very well in determining how many lags we should use. Another approach is to use what's termed as an information criterion in order to decide the appropriate value of the number of lags p in the test regression. And that would work by estimating the value of this information criterion for a range of different values of p. Now, information criteria are really beyond the scope of this course, but in a nutshell, information criteria kind of give you a trade-off between the reduction in the residual sum of squares when we add extra variables into a regression model and the fact that we lose degrees of freedom. So we've already met one good example of an information criterion, and that is adjusted r squared or r bar squared. So adjusted r squared is a good example of an information criterion. So we could use the rule, I'll use the number of lags p in the test regression that maximizes the value of adjusted r squared. Now, as we saw from a previous lecture, there are a number of problems with using adjusted r squared as a way to decide what the model order should be, but nonetheless it is an approach which we could use. Finally, an approach which you may have thought would have been valid, but which turns out to be completely invalid in this case, would be to say, well, I'll estimate a test regression with, let's say, the value of p equals 10, and then I'll look at the statistical significance of the alpha I coefficients in that test regression. Unfortunately, it would not be valid to do this because we have a unit root variable, that is yt minus 1, in the test regression, and therefore it's not valid to conduct hypothesis tests in that test regression about the values of the alpha I parameters. So we can't look at the values of the alpha I parameters and their significances to decide whether those lagged variables should be in the test regression or not. We either use the frequency of the data to decide, or we can use some information criterion. Once again, the best approach is to estimate the test regression for a range of values of p, and hopefully the conclusion that we reach will not be qualitatively altered by changing the value of p. That is, for example, we could use p equals 0, 1, 2, 3, 4, 5 and 10, and we hope that whatever value of p we use, either we don't reject the null hypothesis in every case, or we do reject the null hypothesis in every case. And once again, apart from in the situations where we have very small samples, fortunately the results of the Dickey-Fuller test and augmented Dickey-Fuller tests are not usually sensitive to the number of lags we include in the test regression. Now, if we don't reject the null hypothesis when we conduct Dickey-Fuller or augmented Dickey-Fuller test regressions, it turns out that the way that we interpret that conclusion needs to be thought about a little carefully. And I'll just illustrate why that is the case now. So suppose that we run the test in either of these two forms and we rejected the null hypothesis. If we reject the null hypothesis in either of these two cases, then the conclusion would be that our original series yt was I0. In other words, the original series yt was stationary. What would happen, on the other hand, if we did not reject the null hypothesis? Well, unfortunately, we cannot conclude simply that yt is integrated of order 1. Because the problem is, what would have happened in the context of these tests if we had not rejected the null hypothesis, but the data generating process had been one for an I2 variable? So in other words, suppose that yt had actually been an I2 process. In other words, yt contained 2 unit roots. Obviously, when we ran the test regression here in the levels form, then we would not have rejected the null hypothesis anyway. So the appropriate conclusion here, if we do not reject the null hypothesis, would be to say that the conclusion is that yt contains at least 1 unit root. It may contain 1 unit root, but equally if it contained 2 or 3 or 4 or 5 unit roots, or even more, then we still would not have rejected that null hypothesis. So we need to be careful how we interpret the conclusion in this case. If we reject the null hypothesis, we can conclude that the original series yt was stationary, and that's the end of the story. It would then be valid to use the series y in levels forms in regressions. If, on the other hand, we don't reject the null hypothesis, then we need to conduct another set of tests. And if we were to use this way of writing things on the left here, the next set of regressions that we would conduct if we did not reject this null hypothesis would be a regression of delta yt on the lag of delta yt. And then we would conduct a unit root test in the context of this regression here. Then obviously the null hypothesis would still be the same, and the alternative hypothesis would still be the same in terms of this parameter here, but the way that we would interpret them would now be slightly different. Because we're conducting a test now in the context of a variable that's already been differenced, then under the null hypothesis here, if we did not reject this, then we would conclude that our series yt contained at least 2 unit roots. So under the null hypothesis here, yt contains at least 2 unit roots. Or also under the null hypothesis, we could write that delta yt contains at least 1 unit root. Okay? Under the alternative hypothesis, remember, we already did not reject the null hypothesis in the first case, so we know that there was at least 1 unit root from the first set of tests that we've done. In the second set of tests here, if we do reject the null hypothesis, then we conclude that our original series yt contained exactly 1 unit root. Or in other words, the series delta yt contains no unit roots. In other words, it's a stationary series. So what we need to do, if we don't reject the null hypothesis in a unit root test, strictly speaking, is then to move up a gear. In other words, to take first differences and reapply the test on the first differences. Then if we reject the null hypothesis, again, that's the end of the story and we can draw a conclusion. If we still do not reject the null hypothesis, then what we should then do is move up another gear and run a regression of the difference operator applied twice on the lag of the variable with a difference operator applied twice, and so on. Obviously, if we wanted to, we could write this test regression here using this slightly different format. And you might like to think about how we would do that in practice. Now, it turns out that once again, this is a kind of issue that exists only in theory, but is not really of relevance in practice. As I said before, there's only one series in the whole of economics and finance which some researchers believe could be an I2 process, and that's series like the retail price index. No researchers have ever found any series that they think are I3 or I4. So in practice, if we run a unit root test on a set of time series data and we don't reject the null hypothesis, we can be fairly confident that that process is an I1 process and not an I2 process or an I3 process and so on. So in practice, we only usually actually have to apply this test once. So as I said, in theory, life is slightly more complicated than we might have imagined, but in practice, it doesn't really matter. Now, unit root testing in the academic literature resulted in a large number of papers on the subject. And those papers were, in many cases, concerned with applications of the test and whether series in practice could be best considered as unit root processes or as stationary processes. But there were also a number of theoretical papers which looked at different aspects of unit root testing. And one other approach to testing for unit roots was developed by Phillips and Perron. Now, Phillips and Perron developed a new approach to testing for unit roots, which was very similar in spirit to Dickey-Fuller and augmented Dickey-Fuller tests, but which incorporated an automatic correction for autocorrelated residuals in the test regression. So the Phillips-Perron approach kind of removed the need to arbitrarily specify a number of lags that had to be included in the test regression. Now, the Phillips-Perron approach is not nearly as widely used as the Dickey-Fuller and augmented Dickey-Fuller approach because the Phillips-Perron test is inherently more complex to calculate, and almost always the Phillips-Perron tests give the same conclusions as Dickey-Fuller and augmented Dickey-Fuller tests. Also, when we know a little bit more about unit roots and about the relationship between non-stationary variables, we can have a pretty good idea about whether we think series are going to contain a unit root or whether they're going to be stationary, entirely on the basis of what kind of variables those series actually represent. So, for example, do the series represent what we might call stock variables, where we're measuring the amount of something, for example, the size of a country's GDP, or the size of money supply, or the value of a stock index, or are they what we might call flow variables, that is, the changes to the amount of stock of something over time? For example, asset returns would be an example of a flow variable. So we can often get a good idea about what the conclusions from a set of unit root tests would be on the basis of knowing about those series without actually ever having to do the tests at all. Now, a number of criticisms have been made of Dickey-Fuller and Phillips-Perron type tests. And the most important of these criticisms is that unit root tests tend to have low power in finite samples. What that terminology actually means is that if the sample size that we've got, the number of observations that we've got, is relatively small, then we can end up with a situation where we can't reject the null hypothesis, not because that null hypothesis is correct, but simply because there's not enough information in our sample to enable us to reject it. Now, hopefully we'll remember from a previous part of the course that the power of a test is defined as 1 minus the probability of a type 2 error. And a type 2 error is defined as the probability that we will fail to reject a null hypothesis that was wrong. In other words, a null hypothesis that we should have rejected. So the power of the test is a number of times that we correctly reject the unit root null hypothesis when the unit root null hypothesis was wrong. That is, the number of times we conclude that the series is stationary when in fact that series was stationary, and that's what we should have done. As I said, the problem of the unit root testing approach is that by construction we have a unit root under the null hypothesis. So we may not reject that null hypothesis either because that null hypothesis is correct, that is because there is indeed a unit root in the series, or simply because we don't have enough information in our sample to enable us to be able to reject it. In particular, unit root tests are very bad at distinguishing between non-stationary series, in other words, series that have a value of the phi coefficient of 1 in the autoregressive model of order 1 representation, against series where the value of phi is 0.95. In other words, where the series is actually stationary, but what we might call a persistent series. The unit root tests are very bad at distinguishing between those two cases, and often we end up concluding that the series has a unit root when really the series was in fact stationary. That's clearly a serious potential problem in practice. One approach to getting around that problem is to use a set of tests as well as the Dickey-Fuller or Phillips-Perron tests, which are known as stationarity tests. Now, stationarity tests essentially reverse the null and alternative hypotheses. We can see in the cases here we had a unit root or non-stationarity under the null hypothesis. and this is called a unit root test. But for a stationarity test, the null and alternative hypotheses would be switched so that we'd have a stationary process under the null hypothesis. We could then conduct the Dickey-Fuller and stationarity tests in parallel, and if we didn't reject the null hypothesis with the Dickey-Fuller test because of a lack of information in our sample, because our sample was small, then we would expect, if that were the case, that we would also not reject the null hypothesis in the context of the stationarity test. If, on the other hand, we are not rejecting the null hypothesis because the null hypothesis is actually true, that is, there is indeed a unit root in the series that we're testing, then when we apply the stationarity test, we would expect that we would reject the null hypothesis of stationarity in favour of the unit root alternative. So parallel use of non-stationarity, that is unit root tests of the Dickey-Fuller or Phillips Perron type, in parallel with stationarity tests, gives us a way to get a better idea of why we don't reject the null hypothesis in practice.